All right, so let me tell you something about catastrophe theory and caustics and interference in cosmology and particles and how it all fits together. So if there are any questions, just let me know. I'm happy to talk. So before we go into it, let's do a small recap of catastrophe theory, which is this theory developed by René Thom here in France, which is a very powerful formalism, even though it has nowadays run out of popularity in some fields. But it's very basic, and it is kind of the red thread going through this whole talk. So let's just revise it very quickly. So if you have a function, an arbitrary function of x, then the function also can have critical points. So a critical point of a function means you take the gradient of the function and it's equal to 0. And if you normally study critical points in an arbitrary function, so you go into the jungle, you grab a continuous function and you differentiate and you find a critical point, then you can normally determine the character of the critical point from the Hessian. So you calculate the Hessian, the second order derivative, you calculate the eigenvalues of the Hessian, count the number of positive and negative eigenvalue, and that tells you whether you are encountered a maximum, a minimum, or saddle point. However, if you have a function which is really a family of functions, so you have an external parameter lambda, let's say, which you can vary, then you can find configurations where the determinant of the Hessian is 0. In other words, one of the eigenvalues is 0. And then the classification in terms of the maxima, minima, and saddle points disappears. That basically fails. But as it turns out, René Thom basically formalized something which was being studied already by Newton and by the ancients. They decided, or they concluded, that there are only a finite number of ways in which you can develop a critical point which is degenerate, a critical point for which the determinant of the Hessian is 0, dependent on the number of external parameters and the dimensions of your gradient space. So what René Thom basically discovered is that you have these 7 elementary catastrophes, and these are the different ways in which this function can basically become a degenerate critical point. So that's basically the complete nature of catastrophe theory, and that's the classification of caustics, it's the classification of degenerate points, it's the classification of Lagrangian maps, so it reappears in many different places. And it's kind of interesting that it follows the same logic as the ADE classification, which you might have seen in semi-simple Lie algebras or in theoretical physics, where you also find these Lie algebras, and they are also classified by the same A and the D's caustics. So basically, you can say, well, if I have this function, so that's x to the third minus ax, then A takes the form of lambda. So if A is 0, then you find that this is indeed a degenerate critical point, because if you take the derivatives, then you get x squared. And that's definitely a critical point, because if you substitute x as 0, then you get 0. But also the second order derivative vanishes. And that's basically how the logic works. So you basically have to just extend the notion of critical point from maxima, saddle point, and minima to this list.
So,
yes.
So the illustration.
Yes.
What type is it? This one?
Oh, so basically, so there are different ways to view this all. But what you find is that if you have a manifold, so that's just a sheet of surface, and you project it down, then you can here find that there are here 3 pieces of surface corresponding to one point where you have projected it. And the boundary between the 3 surface region and this single surface region, that's a caustic. So that will be the 4th caustic. So this line corresponds to this form. This point corresponds to this form. So often people say, oh, if I have a dynamical system, then if I have 3 saddle points or 3 critical points, then you have basically local minima. And then what you can do is you can change your external parameters by which you move your system in this space, the parameter space. And as you cross this singularity, then your minima, your system has to maybe tunnel from a local minima to a global minima. Because once you are crossing this line, then the local minima ceases to exist. So that's where catastrophe theory, the name, comes from. So if you, for example, have a bridge, then you can load pieces of rise on the bridge, and then normally a small deviation in your external parameters, which should be the rise which you load on the bridge, doesn't change anything. But there's one moment when the bridge all collapses, and that basically corresponds to crossing this fault caustic. So just as an advertisement for Friday, let's talk a little bit about the classical application of caustics to the cosmic web. And after this, I will build up to the particles which I advertised. So one of the big questions in large-scale structure formation is, well, we start from this Gaussian random field, which is the Planck satellite, which is the perturbations at the time of recombination. And somehow we end up with this very highly nonlinear complex cosmic web, which consists of the voids, clusters, and filaments. But how does this happen? I mean, it's one thing to run an embodied simulation and say, look, it looks similar. It's another thing to understand why they form and to characterize which are the properties of my initial conditions which leads to a wall, a filament, a cluster, and what's its formation time, etc. And what you can do is you can say, well, let's look at this theoretically and let's see how the density field looks like. So if you consider the map from the initial condition space, which is known as Lagrangian space, to the current universe, which is Eulerian space, then you can we maybe get rid of myself?
Well, if you just turn off your camera, I was going to suggest.
Ah, that's a good move.
Sorry about that. We also need to get the video here. Oh no, it didn't disappear. Sorry about
Oh,
that.
it disappeared, but
Down.
I don't need this corner. Oh. It's a touchscreen. Wow, that's fantastic. All right, so what you can do is you can say, I consider the mapping from Lagrangian space to Eulerian space, and that's given by this map. So in terms of body simulation, what you do is you say, every point of my initial condition space has to move somewhere. Well, it moves to xt by moving a distance s. What you now can do is you can say, well, let's calculate the density field everywhere. And the density by conservation of mass takes this form. So you see the density at the point x prime is the mean density of the universe divided by the gradient of the determinant of the gradient of x, which is just a Jacobian. So basically you say my initial space is partitioned into a grid, and I move the grids as the particles move, and then subsequently I just calculate the volume of all the grid cells, which is this determinant, just a Jacobian, and you find that the density is 1 over that Jacobian. We have to sum over all the initial positions which map to the final position x prime you're interested in. So if you evaluate this density field in an embodied simulation, then this is what you find. So you find in a slice through the embodied simulation, you find that there are regions where you have a single stream, where you have only one initial position mapping to that. Then you have positions where you have multiple streams, so there are multiple particles mapping to that position, and these are bounded by caustics. And this is exactly like Sandrine was asking. This is basically the difference between going from a 3-stream region down here or a single stream region or down there. Or if you do it in lensing, you have the difference between a single image and a multi-image region. That's exactly the same thing. So how do these things develop? Well, here you have a dark matter sheet. So the initial sheet corresponds to the initial configuration of matter. As matter evolves, it can be moving towards each other. And what you see is that you here get this multi-stream region. And if you now go on top, you project it down, then you find that there is this boundary between the single stream region and the 3-stream region. This boundary is the caustic. And you have the fault caustic, which was the first in the list. But then you also have these kinks, which are the caustics, which is this higher order caustic. And that's basically what I use in this work. So another thing to note is that if you write the gradient of x, or really the gradient of s, in terms of its eigenvalues and eigenvectors, then you find that the denominator goes to 0 if 1 plus mu is 0. If you actually want to capture the caustics, which are these higher order caustics, which I was showing in this movie at the end, where you have this kink, you will find that you also have to include the eigenvectors. I will talk about that on Friday in detail. So that's the language which we use. If you now take your density field and you calculate the density and you superpose these caustics on it, then what you obtain is this kind of picture. So all the lines here are walls in the cosmic web, which correspond to this caustic. So as I will show on Friday, you can write down the mathematics of this catastrophe theory. You can calculate which elements in the initial conditions will form which caustics. And that allows you to probe the nonlinear dynamics of structure formation up to today. And basically, all the lines here, they correspond to specific conditions in the initial conditions which formed these caustics. So in particular, the red curves correspond to the gust caustics, and the blue points and the green points, like here, they correspond to a higher order caustic, and they will correspond to the walls and filaments in the cosmic web. So this is just an idea to how you can use this very elementary framework of catastrophe theory to probe the nonlinear evolution of the cosmic web. And this applies to the cosmic web, which is kind of the classical physics application. As I will show, this translates also to quantum physics and lens optics, which is something I will talk about in a second.
In this plot, what is BFT?
BFT is the growing mode.
Ah,
So normally we now use the D for growing mode, but since there's a D caustic, and Zeldovich used B in his Zeldovich approximation paper and decided to use the B.
I have
Yes.
a naive question because
Please.
probably I'm a question now. So, does this assume some smoothing of the initial condition?
Yes. So I've taken the initial conditions and I smoothed it with the Gaussian filter.
You have?
Smoothed it with the Gaussian filter.
Okay. On which scale?
So we do it at a range of scales. So if we scale a lot, then you don't see any structure because there's no multi-stream region. And as you dial down the smoothing, you get to see more and more of the structure. But in this application, the idea is that a telescope won't be sensitive to the most light galaxies.
Yeah.
And that way, it is kind of useless to probe and get a skeleton for the most fine-grained elements of the cosmic web. So we really see this in scale space.
So I mean, practice here, you smooth on 1 megaparsec or
Oh, in that
something,
sense. So this is a very poor embodied simulation. So it's 512 cubed simulation for 100 megaparsec scale. So at some point you just run out of resolution.
Mm. And from an academic theoretical point of view,
Yes.
if you did no smoothing, would it mean there would be caustics everywhere? That you have multi-streaming everywhere in space? Because if I would start with the initial condition, which is very noisy,
Yes.
then I could expect if there was power, which probably even in CDM, power will be cut at some scale. But
Yes.
if there was no cutoff, you will have
Caustics everywhere.
it would not
Exactly.
be well defined.
Exactly.
So you need some smoothing
Indeed.
to make everything.
It's just like the circumference of the perimeter of the UK. If you don't smooth it all, then it's an infinite circumference because it's like a fractal-like behavior.
Okay.
So you have to define your smoothing scale to basically set a ruler you are using to measure the distance.
Okay.
And that's just the same here.
Yeah.
We'll talk about that more on Friday, but indeed you need some smoothing in order to get this properly defined.
Okay.
But also this is, I didn't talk about it here, but this is based on Zeldovich approximation. So you also don't expect that to work on the smaller scales.
Sure.
So you are limited by small scales every way, regardless. So this is kind of the classical application. So just to give an idea how you can use this nonlinear, this very elementary mathematics to probe the non-perturbative regime of physical dynamical systems. That's what I would like to talk about in this talk more, is the application to interference phenomena. So if we consider a lensing system, so let's say you have a binary lens, you have two planets circling each other and there is a star behind the system and it's gravitationally lensing the signal, then what you find is that the mathematics of geometric optics is very similar. So what you normally do is you say I have a thin lens plane, so it is the distances of the deflection is the small compared to the radial distance between the source and the observer. Then what you can do is you can approximate the lensing phenomena with a thin lens screen. And what you basically do is you say I have the point on from the source, which hits the lens screen in position X. And at that lens screen position, it requires a geometric term due to the distance the particle has had to move in order to hit the screen in that location. So it's a geometric term in the time delay. And in addition, you find that there's a phase variation, which models the lens properties. So for a binary gravitational lens, you can calculate what this phi has to be. In this case, it will be 2 logarithms in particular. And what you now can do is you can say, well, if I have my screen and I work in geometric optics, then I have to look at the critical points of my rays of the time delay to calculate my rays. So what you do is you say the time delay function, you take the gradient of the time delay function, you equate it to 0. So you're looking at critical points. It's the whole idea of geometric optics. If you solve for Q, which is the point on the sky you're looking at, then what you find is there is this mapping here. So you basically say, well, a point which intersects the lens plane in point Q in this case, ends up on the sky at that and that location. So this is basically the analog of the embodied simulation or your Lagrangian fluid dynamics. It tells you exactly how everything is deterministically moving. And what you find is that the intensity of your lens signal is indeed, again, a similar formula. So you find that you have 1 over the determinant of the gradient of the lens map in this case. So that was the Lagrangian map and structure formation. And what you find is you have to sum over the different images. So if you have a multi-image region, then you have to add all the contribution of the light rays from these different images. What you find is that the intensity pattern looks, for example, a little bit like this. So here you have a single image region, and here you have a 3-image region. And the single image region is separated from the 3-image region by the caustic. So you find that there are a fourth caustic like here, which is described by this A2 formula, which we had at the first slide. And you have these cusp points where you have these kinks in the critical map, which has these singularities, which will be the cusp singularities. And this is something which is very well known and it has been studied a lot. However, with the advent of gravitational waves and fast radio bursts, we're entering a regime where the wavelength is rather long and the source of the radiation is very coherent, by which geometric optics sometimes fails. And it becomes important to also consider the wave nature of radiation to really model what is happening. And the fascinating thing is that this will break some degeneracies which exist in geometric optics. So if you take the same system, so you have a binary gravitational system, let's say you have 2 planets or 2 black holes orbiting each other and they are gravitationally lensing, let's say a fast radio burst, then you can ask yourself, what is the prediction for the intensity now? If you also take into account the interference. And what you find is that you have to do this Kirchhoff-Fresnel integral. So instead of having just a classical evolution, you get an integral over the lens plane, where you get e to the power I, the frequency of the radiation, times the time delay function. So if you are used to quantum mechanics, then this would be like the action, which is a kind of the time delay function. You integrate over all the positions in the lens plane, and this is like a Feynman integral already, but a one-dimensional version. So basically you say, I go from the source to the observer and do it by all possible paths, by 2 straight lines via the lens plane, and I add all the contributions of these up, and that gives me the lens amplitudes. And if you square the lens amplitude, you get the intensity of the radiation. And if you evaluate this, and this is something people discussed for a long time, but they couldn't evaluate it. So you see many papers where they talk about these integrals and try to interpret it, but up to very recently, it was impossible to do this. If you actually evaluate it, then you get this kind of pattern. So you see that the caustics are still inherited. They are inside of this pattern, and that's also what you would expect, because here you are basically summing over 3 critical points. You see that there is a single image region which now consists of these lines, these ripples, and as it turns out, they will be the interference pattern between real saddle points and also complex saddle points. So what you will find is that normally in geometric optics you only consider the real solutions to the critical points of the time delay function. But if you do wave optics, then you will have to include the imaginary solutions to these equations. And then the whole question is, which of the imaginary solutions should you include and which ones you should stay away from? And that's what I will talk about next. So if you step a little bit back and you go back to your school years and you consider integrals, then there is one thing which is something which we do all the time, but you have to be really careful about with these types of integrals. And that's the interchange of the order of integration and the interchange of limits and integration symbols. So what we will talk about lots in conditionally convergent integral. And that's just like this integral. And conditionally convergent integral is a very simple notion. It means that if you take the absolute value inside, it asks yourselves, does the integral still converge or does it diverge? So if you have a typical integral, then the ones we normally use in physics, then it's absolutely convergent, meaning that if you take the absolute value signs inside, it converges. The integrals I'm interested here are only conditionally convergent, meaning if I integrate this, then I will get a finite result up to some definition, which I will get into in a second. If I take the absolute value inside, then you see e to the power I, a real number, is just a phase. So the absolute value is 1, and the volume of R2 is definitely infinite. So you find that if you take the absolute value, then you diverge, and that's no good. So that's known as a conditionally convergent integral. And these integrals you have to be really careful about. So one thing which you will do in any book is you say, let's consider this Fresnel integral, which is the simplest example, is just a Gaussian integral with an I instead of a minus sign. And what you will see in the books is say, well, let's do the partial integral from minus r to r. And let's then take the limit of r going to infinity. This is known as the canoe spiral. And that's basically following this path. So as r goes to infinity, you are slowly winding down this spiral in the complex space, so the imaginary and the real part, so it's really in the complex space. You see that you are winding around, and indeed, you will end up at the blue dot, which is the solution. That's 1 plus I times the square root of pi over 2, which is great. That's what we learned, that's how it works. However, if we extend this now to the two-dimensional case, then you see that there's an x squared plus a y squared. You say, oh, but that's silly, that's an integral which factorizes, because there's no cross term in the x, so you say, oh, that's just the square of this number, and you get I pi. That's fair enough, but I engineered this example such that it has that property. Because you might equally well say, oh, this looks like a radial integral, because x squared plus y squared is r squared. So if I now go to a radial regulator, so I basically integrate over a disk and grow the disk to infinity, then all of a sudden the thing doesn't converge anymore. So this is really painful because you had some integral which you thought you could define using this kind of techniques, but now it depends on the way you chop it up and how you go to infinity. And this shouldn't come as a surprise, because it's something we already learned in conditionally convergent sums. So if we have a sum S, which is from 1 to infinity of the coefficients A, but if you take the absolute value, it is diverges. So this is the condition for an absolutely convergent sum. If this is not true, if this is infinite, then it's a conditionally convergent sum. And what we learned is that you now are sensitive to the order of summation. Just like if you take different regulators, you sum basically the area in a different way. So a very typical example is if you take the Taylor series of the logarithm, then you find that this beautiful series, this harmonic series, emerges. If you now group the elements differently, and you basically say, well, I go for the red one, then 2 blue ones, then a red one, 2 blue ones, then you can rewrite that as a half times the original integral, or original sum. So you find that you can either make it converge to the logarithm of 2, or a half times the logarithm of 2. And it's not a binary choice, because you can show that you can make it converge to anything you like. So if you wake up tomorrow and you say, I would like to make it converge to E, then you basically sort the elements from large to small, and you sort them to be positive and negative, and then you can basically engineer an algorithm to make that converge to whatever you want. So it's not like you either get this result or this result, but by changing the shape of the regulator, you can make it converge to whatever you wish, which is terrible, because that means that this integral didn't really make sense. So what to do? Well, as I will show you, Picca-Lifshitz theory comes to the rescue. So Picca-Lifshitz theory is a theory which is not very complicated, but it's something which has gone under the radar for a long time. So it was already basically known by Arnold in the Soviet Union, but it has only recently been introduced into physics and astrophysics and radio astronomy. And I think it's a very powerful tool which is fun to learn about. So let's just see how it works. So let's say we start with this kind of integral. Here I take R, but it can be any dimensional manifold. So the original integration domain is R, and you have a function of the form e to the power I f. If you want to, you can also add a g in front, but that doesn't really matter, so let's keep it as simple as possible. Let's assume that f is meromorphic, so locally analytic. So when you did complex analysis, you learned about the Cauchy-Riemann equations. Basically, this tells you that the Cauchy-Riemann equation has to hold up to a certain number of singularities. So that's just to make sure analytic continuations work. Otherwise, there's no notion of complex analysis. What you now can do is you can take your exponent, IF, and you write it in terms of its real part and its imaginary part, where x is now a complex number, and you have analytically continued f into the complex plane. Now you can say, well, the real part, small h, determines the amplitude of this exponent. The imaginary part determines the oscillations. So what you would like to do is you would like to start from your original integration domain, and you would like to deform it into the complex plane, such that the small h function goes to minus infinity, because e to the power minus infinity is 0, so that makes it converge. And you would like the capital H to be constant, because if a capital H is constant, no oscillations. The oscillations is really what was breaking the equation. And what Picca-Lipschitz theory tells you is that if you go through this smooth deformation, which using Cauchy's integration theorem, then you can find an optimal deformation of your original integration contour, and that makes this integral into this one. So what you see is that the integral becomes a sum over a number of saddle points, just like we had a sum over a number of streams before. You find that Ni is the relevancy number. That's saying I would like to include this saddle point and I would like to exclude this saddle point. So N is always an integer for integrals. You find that I have pulled out the imaginary part outside of the integral because I just claimed that that is constant along the steepest descent manifold of the saddle points. So normally when you do saddle point analysis, you learn to say, well, locally I treat my exponent like a Gaussian integral and then you just continue. But here it's doing it more rigorously because there's no approximation and it's in constructive algorithm. So what you do is you say, well, I start from my integral, I calculate its real and imaginary parts, I calculate its saddle points, and I sum over all the saddle points. For every saddle point, I determine whether I want to include it by calculating this N. And for each saddle point, I have to integrate along the steepest descent manifold. So you started with something highly oscillatory, you end up with something which is like a Gaussian integral. It becomes a bell-shaped integral. It's kind of magical that you can simplify all these integrals this way. Now the key point, which you didn't probably learn in school, is this Ni can be calculated geometrically. It turns out that a cell point is relevant to this deformation if and only if the steepest ascent manifold intersects the original integration domain. So here you have one of these saddle points. I have noted by sigma. You can calculate the steepest descent manifold with respect to small h, which is the region along which the integral maximally converges. This is the steepest ascent manifold, where it maximally diverges. And that one is the one we normally conveniently shove under the rug. But Picca-Lipschitz theory tells you that if you intersect this K manifold with the original integration domain, you know what N is. You know whether you should include that saddle point in the deformation, yes or no. And then you're done. That's all of Picca-Lipschitz theory. So it's just an extension, a topological extension of the saddle point method, where you know which of the saddle points to include or exclude. And the deformation is exact, so there's no approximation involved. If you would like to do a subsequent saddle point approximation on this integral, then be my guest, then it becomes an approximation. But you still inherit this intersection number, which is kind of key.
You say again on what you integrate?
Sorry?
What are the GA, the manifold?
The G, this?
Yes.
Oh, the steepest descent manifold.
The steepest descent?
Yes, so you start at the saddle point and you look around and you say, how do I roll the ball down the quickest?
Okay.
So you can just write an ordinary differential equation.
But so Ni, is it 0, 1, or -1?
Yeah.
Okay.
But there are cases where you can also have higher integers, but normally
You can have?
higher integers. So there are obscure situations where you can have 3, 4, 5.
How come? How does it happen?
So,
It means you go several times?
Yeah, so basically circling poles and that kind of stuff. But in normal occurrences, it's just -1, 0, or 1, and the -1 and the 1 basically determine the orientation.
Yeah, sure.
So the original integration domain had an orientation, and the deformation has to have an orientation. That is, yes.
Not so sure I understand why I could be 0.
All right. So let's just look at this example. So here you have 3 real saddle points. So this is optics again. So you have a 3 image region. But you find that there are 2 complex saddle points here. And the steepest ascent manifold in this case is this one. And it is this one. And these 2 integration domains never intersect the real line. So they are 0. So it's as simple as that. But as I showed before, I can make these oscillatory integrals converge to whatever I like. So in what sense is this the way you should define it? Well, there is a very nice theorem which I worked out a while ago, which I'm still very excited about. Is say, well, if you have this conditionally convergent integral, which was still defined, and if you go to mathematics book, then they basically say, we stay away from these. So they say these integrals are not integrable. And then they develop all their theories for the integrable functions, but in physics and in astronomy, we have to deal with them. So we have to define them somehow. So what we can do is we can say, well, we take a limit of this integral where we've inserted this regulator in there. And I will define my regulator to be smooth, so analytic, so no poles, no singularities, perfectly analytic functions like a Gaussian. And I would like, in the limit of r going to infinity, I would like it to go to 1. So in the limit of r going to infinity, it has to disappear somehow. Note that you cannot move the limit inside because we have a conditionally convergent integral, and then the limits and the integration symbols don't commute. But what we now can do is we can say, well, let's define it in this way for some smooth analytic G. Let's now do Picard-Lipschitz theory on this F and write it in terms of CBC manifolds. So that's what we had on the previous page. If you now have deformed it in terms of the CBC manifold, it becomes an absolutely convergent integral. So now we can move the limits inside, the G disappears, and you get your deformation. So any smooth regulator will always give you the Picard-Lipschitz deformation result. The reason that we found these strange behaviors here is because we take a sharp regulator by integrating, doing a partial integral from -r to r, or over a square, a rectangle, or over a circle, or an ellipse. You are basically making a very abnormal sharp cutoff, and that's biting you here. So if you take a smooth regulator or an I-epsilon convergence in quantum field theory, you will always get the Picard-Lipschitz result. That this is the optimal deformation because this oscillations go away. So we can do this. We can do the partial integral like this, and then we had this Cornu spiral. Interestingly, if you just smooth with a Gaussian vector like here, then it not only makes it better defined, but it also converges a lot quicker. So here you see the red curve, which basically arrives at a solution at far smaller r because there are no oscillations. So it's just more, the theory likes this definition more in a sense because everything is downhill. You have the wind in your sails, so to say, once you do this smoothing thing rather than this sharp cutoff. You can do this also numerically. So if you have this lensing potential, then you can discretize your original integration domain on lattice. Now you can move the lattice into the complex plane by flowing it downwards with respect to the real parts, or the small h function we had. And you can numerically find the optimal deformation of your integration domain quite efficiently. So now the integration along the real line was a mess. But after you have deformed the integration domain to be the blue line, the integral becomes as simple as integrating a Gaussian. So you also numerically make the integral tractable. Note that if you flow downwards, you don't have to know the saddle points beforehand, and this intersection algorithm is all automatic. Because normally you would say, oh, if I do Picard-Lipschitz theory, then I first need to know all the saddle points, maybe there's an infinite number of them. Which one should I consider first? If you start from original integration domain and you just flow downwards, then all these problems go away. So this is kind of the numerical implementation of this idea. And that allows you to evaluate these integrals very efficiently. So what used to be very computational nightmare becomes now something you can do on your laptop. You find that there's these caustics again. where the nature of the interference pattern changes. Here you have a 3-image region. You have a single image region separated by these caustics. You find that you have the fault caustics, you have the caustic where you have a kink. And in addition, you find that there are Stokes lines. That's something I didn't mention before. Stokes lines are places where the intersection number changes. You can have situations where a complex settle point first has a steepest ascent which intersects the original integration domain, and you change the external parameters and all of a sudden it doesn't intersect anymore. So here you go from 2 relevant settle points, one real and one complex, to a configuration where you have only one real relevant settle point. And this transition happens through a Stokes phenomenon. So I just wanted to mention it because it's definitely there. It's an integral part of the theory. But since it's not so visible as caustics, I won't dwell on it much more. But just to say, there is this additional kind of complex version of the caustics in some sense. So let's now go to the core. Path integrals. So we did these length integrals, which is e to the power I and time delay function, but it only is a one-dimensional integral. If you want to do quantum mechanics, if you transition amplitudes in cosmology or in particle physics or wherever you want, you have to do a little bit more because it's no longer a one-dimensional integral, but it becomes an infinite dimensional integral. And the question is, how much more difficult is this? So path integrals are kind of our golden tickets to theoretical physics. Yes.
Maybe before you go to
Yes.
more complicated things.
Yes.
In practice,
Yes.
I mean, one problem is that here you can do this because you know exactly the functional form of your integral.
Yes.
Here you put a quartic polynomial or whatever. But if in some practical application I have oscillator integrals, but I know the function f only on some data points on the real line.
Yes, very good.
And then I don't know how to expand to complex space, and presumably there are infinite many ways to do that, and the result will depend on what I choose. No,
you're right, except for your last.
I mean, if I only have a finite number of points on the real line, I can.
So what I've done before is I've said, well, if you have, for example, a random lens, you have an interturbulent media, so interstellar media, which gives you the lensing pattern, and it's a radiation Gaussian random field, for example. Then you can ask yourself, how do I do this analytic continuation? Because that's not well defined, as you said a second ago. What you can do is you can try multiple different interpolation functions, which are analytics. Radial basis functions are ideal, so you take sum of Gaussians, or you take sum of basis functions to model your numerical data points. And you can do Picard-Lipschitz theory on that. And what you find is that depending on your choice of interpolation function, you will get a different number of relevant settle points. But afterwards, the integral is the same. So if you have a small change in your data point, or a small change in your interpolation function, then the interference pattern will smoothly deform a little bit. But it's still very doable.
So you mean it's robust?
Sorry?
You mean it's rather robust because I would expect, for instance, if I have points on an interval, I can use different polynomial.
Yes.
And there will be points or singularities at different places. And I would have expected that the result would be sensitive to where I put the singularities.
So luckily it doesn't. So I've tried it out numerically, and it's
in practice it works.
Yeah.
You say.
Yeah. Okay. So all the intermediate steps look completely different, and then at the end of the day you get the same result.
Well, either way, it's reassuring, but okay, we don't expect that, but okay.
There's a question.
I know I was thinking to what Patrick said. So in terms of why it works so well, even not knowing basically the very fine details of your function on the real plane. Like, how do you understand? Okay, so
you can see it as a clock, and then basically the time delay function will be the time you wrap around in your clock. And if your time delay function changes a little bit, then the final position of your arrow of your clock will change a little bit. But that's kind of a smooth change. That's only a small change.
So in a way it's really like a regular or like when defining a base integral. If you change the function a bit, it doesn't.
Yes, but the analytic continuation changes completely.
Yeah, exactly. Yeah.
So that's kind of so I agree that's not guaranteed. It's not something which you can easily appreciate. But in all the examples I've tried it numerically, it just...
So, for curiosity, so what kind of set of basis function you use to go
I
to
often
this,
take a sum of Gaussians or
sorry,
some
quotient?
Gaussian functions or Lorentz functions, so 1 over 1 plus x squared.
Which are quite different because the
Yes.
quotient, so it will diverge.
Yes,
some,
yes. So that's why I choose these different functions which have completely different properties in the complex plane.
Yeah.
And they give you the same result. So if you take a Gaussian function, then you find normally that you have to include an infinite number of critical points, because you have an essential singularity at complex infinity. Whereas if you have a rational function like 1 over 1 plus x squared, something like that, you find that you have two poles at plus or minus I, and then the whole analytic continuation dies off, because if x is very large in magnitude, and it's just 1 over r squared basically, and then you find that the contribution is 0 at infinity. So the Gaussian and the Lorentzian function have completely different properties in the analytic continuation, but on the real line they are very similar.
So you're saying rational functions from a practical point of view are more efficient?
Yes.
Because of
because you have a finite number of saddle points, and it's easier to control its behavior at large x. But
Yeah.
but both work. I mean, it might be a little bit more tricky, but you get the same result.
Okay.
Otherwise, it all would collapse. I completely agree.
Okay.
All right, so let's talk a little bit of path integrals in the remaining time. So what we often do is we describe these path integrals, and then you say, well, I have e to the power I over h bar, and then you have the action. And basically in the action, you can put all your physics. So you can say I have Einstein gravity, I have a Maxwell field, I have Lagrangian for dark energy, and that's basically the formalism which we use. But then the question is, what is the measure? Is this integral even well defined? How do we evaluate this in practice? It's a horribly oscillatory integral because there's an I here, so often people do a wig rotation, but then you go to imaginary time, and how do you use that to describe evolution in quantum systems? So there's a lot of confusion there, and it's a very exciting field, in my opinion. So what you basically do is, in most elementary form, following Feynman and Hibbs, you can just restrict yourself to quantum mechanics for a second. You say, I consider the transition amplitude to go from x0 to x1 in time t, and you say, well, that's the path integral like this, whatever that means. But the idea is that you consider all possible paths to go from A to B. So this is one path, but you consider all possible paths, and you, for each path, you calculate the action, which is kinetic energy minus potential energy integrated over the time, and that gives you a number, just like what we had for our length integrals. And then we sum it up, and then we get the amplitude. If you square the amplitude, you get the probability to go from x0 to x1. And the reason Feynman really liked that, because it basically shows that classical physics emerges due to constructive interference, just like geometric optics emerges due to constructive interference from the Kirchhoff-Fresnel integral. But how should we evaluate this? How can we actually use this? Is it even meaningful to talk about this infinite dimensional integral? So the path integral is instrumental to many fields in physics, but also in particular quantum cosmology or quantum gravity, where Wheeler in his geometric dynamics already basically described how you can extend this from a world line to space-times, and you can hope to really describe the amplitude to go from one universe to another universe, as in time evolution, so 3 geometry to another 3 geometry. So this was my original motivation to look into this. But what's the problem? Well, in Feynman and Hibbs, which is, I think, kind of the Bible of path integrals, because the first book, they already noticed that there are conceptual issues. And they say, well, let's go forward anyway, because the ideas are normally more important than the mathematical definitions. So they say, well, let's really treat it like a physicist. But we're now so many years beyond Feynman and Hibbs, and let's try to make sense of that regardless. So before we go into the details, I have to talk with you a little bit about problems. And in order to do that, we have to do a little bit of formal measure theory. So if you want to define an integral, you need to define a measure. And a measure is basically describing the size of a set. And in order to describe this measure, we have to describe the sets, because we have to define a function from the sets to the real numbers, or the complex numbers if you want. And you have to decide, from which sets do I need to do this? So what you first need is a sigma algebra. And the sigma algebra is basically a set of subsets of a big set omega. So this will be the real line for us often, or the space of paths, or whatever you want. And you say, well, I would like the whole set to be in my sigma algebra. So I would like to give a number to the size of the whole set. I also would like to say, if I have a subset in the algebra, so I have a small piece of space, let's say, for which I would like to find my measure, I also would like the complement to be in that space. That's also a fairly simple and innocent condition. And the third condition is that if you have a set of sets, a countable number of them, then the union has to be also in the set. This is basically what is a sigma algebra, and we take it for granted every day because all the integrals we do normally behave like this. Then when we have our sigma algebra, we can define the sigma measure. And sigma measure is a map from this algebra to the line 0, infinity, which such that the empty set is 0. No, the empty set has to be in A because the whole set is in A, and the complement of the whole set is the empty set. So that's good. So we can say mu of the empty set has to be 0, and that's basically saying, well, if I would like to measure buckets of water and I have an empty bucket, and I would like to say there's 0 water in that. You would like to say that if you have pairwise disjoint sets, an uncountable number of them, so you have an uncountable set of buckets which you have, and you want to say, well, if I take the measure of all the buckets and I sum it up, then it has to be the same as me putting all the buckets in one bigger bucket and taking the measure of that. So this is all very innocent and all very nice. Once you have this measure, then you can start to define your integrals by limiting series. So you can say, well, if I take basically an approximation by step functions of my integral, either from below and from above, and then you can create the limiting procedure of refining these boxes, and then you can hopefully approximate your continuous function, and that gives you your measure. Note that the Lebesgue measure we normally have is translational invariant. So if I take this region, this disk, and I calculate the area of it, and I move it a little bit to the right, then it has the same area. If I have a bucket with water and I move it to the right, then it's still the same amount of water in there. And that's the problem. So the translational invariance of the Lebesgue measure, which is very nice and intuitive, makes the infinite product of Lebesgue measures, as you see in all the quantum mechanics books, sick and ill and problematic. And what you basically can do is you can see it in multiple ways, but the simplest way I find is that if you take the unit cube in an n-dimensional space, then the measure has to be 1, because you take all the x's and you multiply them together, and 1 times 1 times 1 times 1 is 1. If I now subdivide my box along all the dimensions by 2, just half, then I get 2 to the power n of these boxes. And if it's translational invariant, then I can all move them basically back to the simplest box, which had the corner at 0, 0, 0, 0. So what you find is that indeed 1 is the measure of this unit cube, is equal to 2 to the power n, is the measure of the smaller cube. But if you now let n go to infinity, which we often want to do in quantum path rules, then you find that in order for this to be still 1, the measure of this smaller box has to go to 0. So all of a sudden, if we have translational invariant measures, they don't really work well with infinite dimensional spaces, because they become, say, that all the sets of paths, which we will consider in a second, will have measure 0, so they don't occur. So this is basically the reason why mathematicians often say path integrals don't make sense. That doesn't mean that you cannot have a well-defined sigma measure and a well-defined measure on paths. So the Wiener integral, or the Brownian bridge integral, is an example of a well-defined integral, which is fully accepted in mathematics and which makes perfect sense and satisfies all the criteria. And it does it by getting rid of this translational invariance, because that was really the reason that the infinite product of Lebesgue measures has problems. And what you can do is you can say, well, let's consider a space of paths which go through a certain set of windows. So I go from 0 to 0, and I pass through these different windows. So it's like you open your window in your room, and you say, well, the particle has to fly through the number of windows. Or if you do a double slit experiment, you say the particle has to flow through the slit. Then you can say, well, the measure of the paths going through the slits can be written in this kind of integral. We see that you have a series of Gaussian kind of integrals, but with a minus sign. And this is what Katz and Feynman used to define the Feynman-Katz formulation of the path integral in Euclidean space. So if you start with your horribly oscillatory integral and you recrotate to complex time, then you get a minus sign. And now you can rewrite that in terms of the Feynman measure, or the Brownian measure, whereas this is the well-defined Brownian measure. And you basically see that the kinetic term gets absorbed with the measure into this measure. So basically the translational, the fact that the kinetic term is not translational invariant basically leads to that you have a well-defined measure. So this is what people often do when they talk about real time, imaginary time, quick-rotated integrals. And this is perfectly well-defined and very nice, but it doesn't allow you to say, I go from here to tomorrow, because you have gone to imaginary time, and you have gotten rid of all your oscillations, all your interference, by doing this quick-rotation. And what I will talk about in the last few minutes is that you can actually do this.
You don't have to have,
right.
You don't have strict maybe.
All right, so then it will take a little bit more time. So what you can do is say, well, we can use the same logic, combine it with Picard-Lipschitz theory to get a well-defined notion of an integral for real-time quantum mechanics. And what you basically find is that you can start from your infinite dimensional or your time discretized integral. You can add your smooth regulator. You can then apply Picard-Lipschitz theory to that. You deform the integral into the complex plane. And what you obtain is something very similar to what we saw in the finite dimensional case, where you have basically instanton contribution. So you have e to the power I as of the classical path, but it now can be a real classical path or a complex classical path interpolating between the two boundary conditions, x0 and x1, in time t. And what you're left with is here an integral along the steepest descent manifold of this instanton. And what you find is that you can define the integral along this steepest descent manifold into something which is related to this Wiener measure. So if you do everything on the real plane, then you have to do a wave rotation in order to apply this Wiener measure to make it make sense. But if you combine that with Picard-Lipschitz theory, it gives you enough elbow room to basically do the same trick. But now it's real interference. You have nowhere an imaginary time, and you find that there are these contributions I everywhere, and you find that all the classical paths are relevant. So just like what we saw in lensing, where you find that the pattern of your interference pattern changes, the quality of the interference pattern changes whether you are in the single image region or the three image region, and where you find that outside of the fault caustics, you find some oscillations which have to do with a complex level point, which was relevant due to this intersection algorithm. This is basically the infinite dimensional version of that. Yet this is just a mathematical formula and it's not very useful.
Yes. Sorry, so I guess I missed some points. What you call the Wiener measure,
yes.
Is it the Brownian motion or
yes.
something different?
The measure of Brownian motion.
Okay, so it comes from the same thing.
Yes, yes, yes. So you say, basically you say, well, I start my Brownian motion at 0.
Yeah.
I now only consider the paths from the Brownian motion which end up at 0.
Yeah. So
it's just a selection effect. Yeah. And then once you have such a path, you basically can say, what's the probability that I find that's a path? And the probability is of course 0. But if you say, what's the probability that I pass through these windows? Then that gives you a probability, and that's exactly the...
Okay. Okay.
So you can treat Brownian motion as a particle which hops by steps.
Yeah.
Or you can say, I would like to understand it in terms of a probabilistic distribution.
Yeah.
And that's it.
Okay.
Shall I continue? Or?
I had another question. So
sure,
on
please.
your next slide, yeah. So here, so in the first part of your talk, you had this n
yes.
0, 1, minus
yes,
1.
Yes.
Here,
it's secretly in there. I only summed over the relevant ones.
Okay, and so, you will explain how you find them.
Yes, yes,
okay.
yes.
Now, why does your measure depend on the the relevant solutions.
Um, so the measure doesn't depend on whether the saddle point is relevant. But if the saddle point is not relevant, so that steepest descent manifold is not part of the deformation, then you just don't include it in the sum.
Okay, but so the probability measure
Yes.
has an index.
Oh, yeah. So every saddle point, so you basically can look at what the action does around the saddle point.
Okay.
And that determines how to measure. So this is not directly the Wiener measure, but you can relate it to it.
Okay.
So it's all a little bit less explicit than the Feynman Katz result, but then you can do real time.
Okay.
But this is a very nice formula, and it shows that it in principle works, but it doesn't tell you how to do the calculation. Because you can have an infinite number of saddle points, and doing an infinite dimensional integral over the real plane is already a mess. This does show that it works, and you might be able to use this in resurgence theory, which is something I won't talk about, to progress beyond just this formula to make it in something numerical. But I found another way of doing it, so that's what I will talk about next. So I derived this formula 4 years ago, and then I thought, well, I would like to show what the path integral actually looks like in practice. And I don't really like the time discretized path integral because there's all kinds of artifacts which you introduce, but I have no better way, so let's do it anyway. So if you go in Feynman and Hibbs, then you will see that the path integral is defined in terms of an n-1 or an n-1 dimensional integral. So what you do is you have this prefactor, which has something with the potential at the boundary points. And what you find is that your action basically becomes this enormous set of terms, where you see that this is basically due to the kinetic term, and this is due to the potential term. I'm missing a bracket. And what Feynman and Hibbs do is they integrate over all the intermediate times. So you say I go from A to B, I add a number of slides at the different times. I consider basically stick figures of my paths moving between these different times, moving from x0 to x1 to x2, x2, x3 till you reach qn-1, and then you get to your final condition. So this is how the Feynman path integral is normally defined. So you say this is gm, and then you take the limit of n to infinity, and you get the integral. And this is a very nice formalism because it's very explicit, but it's a nightmare to evaluate. Because we already were suffering from a one-dimensional oscillatory integral, now you have an infinite dimensional one. So how to make progress? So what often people do is they do a Wick rotation. You go to imaginary time, you change this I into the minus sign, then you have a high-dimensional Gaussian-like integral, and then you can hope to do Hamiltonian Monte Carlo on that. But that's not what I want to do, because I would like to do real propagation. I would like to say, what does it mean to go from x0 to x1 in finite time? So I would really like to evaluate this thing by evaluating this integral. Many of the lattice field theory books will say this is hopeless, so let's do a Wick rotation and let's carry on with our lives. Here I would like to show that this integral is actually doable. So here it's an r and a d n-1 dimensional integral, where n is the number of time slices and d is the dimension of your slice, so the dimension of space. And what we can do is you can say there is a certain structure in there which allows us to write this as an iterative integral. Yes.
Sorry, I have a very naive question because you are going back to basics. And,
yes.
So you have this expression. You say indeed it's not very convenient.
Yes. To say the least.
Yeah. But I assume that this proprietor of this function, it also satisfies some differential equation.
Yes.
So
yes.
Isn't it another way to?
Yeah. So this is the Green's function of the Schrödinger equation.
Yeah.
So you basically have an object which satisfies the Schrödinger equation with respect to both x0 and x1, with the boundary condition that if you let t go into 0, it becomes a Dirac delta function.
Yeah.
So that's another mathematical definition, which has nothing to do with path integrals.
Yeah.
But numerically calculating that is also a mess. Because if you want to implement the Dirac delta function, then it becomes difficult because you're discretizing it on a lattice.
Yeah, but I assume there are probably ways. So you say trying to compute it from the differential equation is not easier than trying to deal with the integral.
Yes.
I know, it's not easier. Okay.
In general cases, it's not easy at all. Solving the evolution of an initial state is a lot easier. So if you start with a Gaussian state or some wave function and you propagate it forward in time, then that's very easy. That's something we can.
But Dirac, you could. I mean, in practice, you have to smooth it somehow on the computer.
Yes. So here you don't.
Yeah. Okay.
So it's just a complementary technique. So if you just want to see the evolution of a wave function, then there are better ways of doing it. But I would like to extend this, for example, to quantum cosmology, where we cannot do that. So I completely agree that there are realms of applicability where other tools are more useful. But if you just want to see what's the mathematical property of this propagator, then I don't know a way of doing it. Except for when you have can solve the time-independent Schrödinger equation in closed form, and then you can use a spectral representation to do that. But then we only have a finite set of theories for which you can solve the time-independent Schrödinger equation in closed form.
Okay.
So what we can do is we can write it as an iterative series where you just say, well, let's do first the Q1 integral, and then let's do the Q2 integral, let's do the Q3 integral. And what you find is that you start with this integral of this formula, which is like a Gaussian. And then what you find is that you have to basically take the previous I and multiply it by this oscillatory function and integrate that over Qn. And then you just keep doing that till you reach I capital N, and you multiply it by this prefactor which we had here, and you're done. But this is not simplifying anything because it's just rewriting a horrible integral into another horrible set of integrals. But what we can do is we can make a little bit of progress, because you can say, well, let's do the Q2 integral, which was the Q1 integral first. So that's just writing out this integral formula for n being 1. So that's this thing. Well, this is just like the length integral we had before. So you can do this with Peter-Lipschitz theory numerically. You can deform the integration domain into complex plane, you can evaluate it numerically, and you get some numerical result. What you can do is you can say, oh, I can also do a saddle point approximation on this one-dimensional integral or this d-dimensional integral. And I can basically approximate the saddle point approximation by this formula. So this formula basically tells you what I2 is doing for large Q2. What you now can do is you can rewrite this numerically evaluated result, which is I2, as a sum of this analytic result plus some numerical result. So since we know this one and this one, we can calculate this delta I2 to compensate for the error we made in this approximation. But now, since J2 will approximate I2 for large Q2, which you can see here, so it goes to 0 for large Q2, we know that this delta I2 will go to 0 for large Q2. And now what we can do is we can substitute this formula into the iterative step in here. And what you're left with is a sum of two integrals. You can integral over the J contribution, which is this analytic form, and you get an integral over the delta I2. But this is an integral we can do with Peter-Lipschitz again, because everything is analytic, and we can continue in the complex plane. And this is an integral we can do numerically very efficiently, because since delta I2 goes to 0, you can just evaluate this with two Fourier transforms. Now you're done, because you can do one step to the next step, and you can just keep iterating, and you get your final integral. So in practice, if you rearrange this, what you can do is you can calculate a series of n d-dimensional integrals, which is of this form. And this is something you can do numerically using Peter-Lipschitz theory by deforming the original integration domain into complex plane. And what you can then do is you can calculate delta I2 by subtracting the j, which we had. And then you can iterate in I by basically following this step. So you have the j, which we calculated here, and you add this numerical step, which we can do with two fast Fourier transforms. And after you've done it, you have calculated your IN, and you can see how it looks like. So this is the absolute value of the propagator at fixed time as a function of x0 and x1 for 5 integration steps in time. We have discretized your patterns rule in 5 steps. This is for Rosen-Morse barrier. So you have a potential barrier, which is a little bit like a Gaussian shape. And you can consider the propagator to go from x0, x1 at finite time. So time is 10 here. Say if I have 5 intermediate steps in my discretization of a patterns rule, then it looks like this. If I take 10 steps, it looks like this. If I take 15 steps, then it looks like this. So you see there are all these caustics, all these cell points, which are just artifacts of the discretization, which goes away if you go to larger n. And if you do calculate the propagator exactly, so I've chosen a potential for which you can do it exactly using spectral representation, then you get this. So you see, you approach the exact results. And if you now do this, calculate the difference as a function of the number of integration steps, then you see that it converges rather quickly. So for n is 20, by I you don't see the difference. You see, you can also go for, let's say, 1,000 intermediate slicings of your propagator, and you converge rather quickly to the exact result. So now you can actually evaluate these pattern rules, and you get the same kind of caustic interference pattern we saw in lens optics. And as far as I know, nobody actually studied these pattern rules as in, let's evaluate them and let's see what happens. And what you actually can see is that if you identify the caustics, which are the caustics of the classical system underlying your pattern rule, which is just like caustics from geometric optics, which are inherited by the wave optics lens, then you can actually predict what happens to the evolution of a Gaussian wave package. So you can say, well, if I've taken a Gaussian wave package, which is centered at some location, and I propagate it for so many units of time, then it becomes a wave package between these and these positions in space, which match exactly up with the caustics. So you might not care about it, but I thought that it's really fun to see that this is not only an artifact of the propagator, but it actually describes how your wave packages will be evolving when you numerically solve it with a Schrödinger solver. Yes.
On the previous slide,
Yes.
or maybe the one before, it's a bit counterintuitive to me because you first say, okay, I decompose J bar and delta I.
Yes.
Because for large Q2,
yes.
Delta I is going to be small.
Yes.
I assume that's correct.
Yes, that's correct.
But then when you increase the discretization, I mean,
yes.
you will increase the number of points.
Yes.
And which means your delta Q will get smaller.
Yes.
So it looks a bit like, okay, which goes in the wrong direction. So it's a bit, it's not clear why it works. I assume it works, but it's not clear to me why.
Yes, so I don't have a theoretical proof that it will work. So I developed this first for multi-plane lensing, so I didn't say that. So I worked this out for one-plane lensing, as I showed you. And I thought, oh, let's do multi-plane lensing. And then only recently we thought, well, let's see what happens if you take an infinite number of lens planes. And it was not guaranteed that it will converge, as you say, because this limit might not be ill-defined. But it turns out that this J2 becomes actually better as you take more integration steps. So I don't have a mathematical proof why the convergence works. So I'm just saying that if you do it, it turns out to work. So I don't have a theory for which it doesn't work.
Okay.
So if you consider not a potential barrier, but the potential well, then you find that there are a number of reflections you can make before you go from H0 to H1, which gives you a whole set of nested caustics. And just for fun of it, you can change H bar, so your Planck constant, and you see that you can recover more and more of the interference pattern of this caustic pattern, which I find fascinating. So based on such a figure, then you really see that the real classical paths are ingrained in the patterns rule, which I find fascinating. So it allows us to probe it in a different way. And just since I'm already a little bit late, let's.
No, but really, I think we can go through.
All right, all right. Okay. All right, so let's then take the final step and say, I can now evaluate the pattern rule numerically. But how do we find what are the relevant settle points? So we had before this intersection number, and you correctly asked, how do you determine that? So one way in which you can determine it is look at the caustic pattern and the Stokes phenomena. So one way of doing it is we can, using the classical equations, we can look at caustics. These were the red lines in the previous plot, where you look at the evolution of a classical equation. So this Newton's laws, mass times acceleration is the force. So if you solve that, then you can look for the caustics, and you can calculate these, and that basically corresponds to the black lines here. And you find that at the cusp caustic, you have these Stokes lines which go out. And this is something you can compute because you know that at the Stokes line, the imaginary part at the settle points which are intersecting or which are basically connected here, the imaginary part of the exponent will be 0. So in path integrals, the real part of the action will be the same between these two instantons, these two settle points, when you go through this Stokes phenomenon transition. So one way you can do it is you can calculate the caustic pattern, and then you can subsequently keep track of all your settle points and see where the Stokes lines are happening. And then you can read off the intersection numbers. So note that the intersection number can only change when you're crossing a caustic or a Stokes line. So it's not that you have to calculate it independently every time when you consider every position x0 and x1 a fixed time or as a function of time. It's really a topological thing. There are really regions where the settle point is relevant, and then other regions where they are irrelevant. And the boundary of these regions are these caustics and the Stokes lines. So if you can keep track of the boundaries, then you can basically fill in the picture afterwards. Just like a child, you have maybe a painting you would like to draw in, and you already have all the lines. You can just take your crayons and say, oh, I would like that region to be blue, I would like that to be red. So that's in theory one way in which you can calculate this intersection number. But there's another way, which is a more numerical way, which I have worked on recently, which I find really exciting, because then you can check whether that is actually true. So if you consider, for example, a step potential, smooth steps, so this is known as a Woods and Sachs potential, then it looks like this. So it's just a very simple step. It's kind of the simplest quantum mechanics problems you encounter when you learn about quantum mechanics. And it's a very nice theory because you can solve the time-independent Schrödinger equation. So for a heavyset step, it looks like this. These are the energy eigenstates. But also in the smooth version, you can write them in terms of special functions. The name escapes me at a second. But the point is that if you can solve the time-independent Schrödinger equation, you can insert that into the spectral representation of the propagator, where you get two products of the eigenstates. You multiply it by e to the power I energy times time over h bar, basically. So either you solve the propagator using the stitching method, which works very nicely, or you do it with the spectral representation. And anyway, you can calculate numerically this propagator. Then what you can do is you can say, dear propagator, what are your relevant settle points? The real settle points are automatically relevant, because if the real settle point lives on the original integration domain, so the steepest ascent of that settle point will obviously intersect the original integration domain. But the complex settle points, it's an open question. That's kind of question multiple people in different fields are currently hanging their heads against the wall, trying to figure out, when do I determine which settle points to include and which settle points should I not include? So what I recently proposed is to say, well, let's take our propagator. Let's take omega to be 1 over the Planck constant. So that in lensing, that would be just the frequency. And let's take our propagator and do a Laplace transform or a Fourier transform. Both are relevant with respect to 1 over the frequency. Because if you take the WKB approximation, then you find that your propagator is basically a sum of e to the numerical factor times e to the power I, the classical action, divided by h bar. So if you use omega, then it's e to the power I, the classical action, times omega. But that's just like a Fourier mode. So what you can do is you can do a Fourier transform of your propagator, which you've calculated numerically, either using the stitching method, or you're lucky enough that you can use the spectral representation, you can do it that way. if you would do a WKB approximation of the propagator, then you get a sum over the relevant saddle points. So I've only included the saddle point where n is actually 1. And what you can do is you can do the integral over omega, and you find that you get something which is approximately of this one. We see that if t is equal to the classical action or minus classical action, this thing spikes. And if you do this numerically, then you get these kind of patterns. So if x0 is minus 5, you propagate this for a step, this is the heaviside step, for 5 units of time or 10 units of time. And you look at what the propagator is as a function of x1. And then you do the Fourier transform with respect to 1 over h bar. You get this kind of pattern. And as you do it for different x1s, you screen this pattern. What you find is there is a peak here and a peak here, and here there is something which is difficult to see for the heaviside step, and there is a peak here. What you can do is you can look at your real classical solutions to the boundary value problem from classical mechanics, and you can calculate the action of all the paths which you find which are solutions to the boundary value problem, and that gives you the blue lines. So you can read off the real classical paths from the propagator. That's no surprise, otherwise the classical limit would never emerge. But in addition, you find that there's a peak here and a peak here. And this stripe doesn't have a classical path analog, but it does have a complex classical path analog. So you can read off the relevant complex classical paths from the propagator after you've evaluated it. Of course, you can say, I don't care about the complex classical paths after I've evaluated my propagator anyway. I personally find it useful to have a way to check that the relevant saddle points which we have identified, the complex relevant saddle points, were actually relevant. So this is a numerical way to do this. However, there is a kink in the cable. So normally people consider these complex classical paths to be the say-it-all, that's the way we describe quantum tunneling. But yet, there are very few examples for which people have identified these instantons, these complex classical paths, for finite time propagation. So let's say quantum tunneling through a barrier. So this took us a year to figure out why this is, because it was completely paradoxical for us. Is what you can do is you can say, let me consider the situation that you go from x0, let's say at -5, to x1 being 5. For 10 units of integration time. And you can consider the space of complex classical paths by considering x0 to be the initial position and the initial velocity to be some complex number. And depending on the value of your complex number, you will either arrive at complex final position or in real final position. So if you paint in the real final positions, then you get these blue curves. So if I say I would like to go from x0 to x1 with some complex velocity, and I would like the final position to be real, but I would its real part to be a certain number, then you basically can see that as you change x1, the final position of your particle, gradually, then you see that you are moving in the space of complex initial velocities. There's no surprise there, but if you smoothly change the boundary conditions, then the complex classical paths have to change smoothly. But what we find is that the cell point, which is here, it moves to this position as you change x1, as you are trying to recover the tunneling amplitude, the complex classical path responsible for the quantum tunneling. But before you actually do quantum tunneling, before x1 actually becomes positive, if you start from negative, you hit this wall. And this is something we got really puzzled about. So what we did is we said, well, let's look at the complex classical path as we are approaching this point. And that's what you see here. So you see that first you go like this, so it's like a real classical bounce. Then it becomes a bounce like this, and at some point you hit the singularity of analytic continuation. So your potential, which is here the smooth step, which is a 1 over. It's basically tension potential. The tension function has singularity in the complex planes, and here you see these singularities. And what you find is that your complex classical paths hit these singularities. So after you go beyond this barrier, you can look all you want for an instanton which solves your tunneling problem, but you will not find it. What happens to be the case is that you have to consider the analytic continuation of this instanton while you are changing x1 in order to find it. And once you include that, the WKB approximation starts to make sense again. So you can see it like this, where you say, oh, I have to do some analytic continuation. You can also make it more formal. You can say, I consider the paths, an equivalence class of complex classical paths, where not only X can become complex, but also T can become complex. Because the action, which is the important phenomenon in quantum mechanics, is an integral over time. And if you change the integration domain over that time integral, keeping the boundary points fixed, and you keep the action the same, and you can basically build this equivalence class of paths. And you find that here, what happened is that the member of this path, which corresponds to real-time propagation and not along a complex contour, that ceases to make sense. So it's not only that we have to say there are cell points which were there but which are not relevant, but there are also cell points which are kind of hidden behind these branch cuts. Because once you interpret it like this, then it's just a branch cut. And as we know, branch cuts are arbitrary. You can move them around as much as you want. So this changing the contour in T, going from 0 to capital T, is basically moving these branch cuts around when you solve your boundary value problem. And that allows you to recover the instantons. And that way you can find your instanton, you can find your complex classical solution, or really your equivalence class of a complex classical solution, which recovers your quantum amplitude for the quantum tunneling at finite time. So this is something we are currently looking into. So if you apply this to quantum cosmology for the Big Bang, then you find that your analytic continuation of your action looks a little bit like this. The original integral was from 0 to infinity. This is the integral over the lapse. Hawking and Hartle said, well, we don't know which of the cell points to include. This is in the 80s. For the propagation of the universe from nothing to our universe. So there's no boundary proposal. The idea is that a nucleation out of nothingness. So they didn't know which cell points to choose. So what they did is they said, what is the one which makes physical sense? It's a very good thing to do. If you don't know how to do this oscillatory integral, then you might as well say, well, which one is the most plausible one? Unfortunately, they found this cell point, whereas if you do Picard-Lipschitz theory, then you start from the integration domain like this. And if you deform it downwards, then you find that this is the proper contour. And unfortunately, this gives you the nice properties with respect to inflation for the zero mode of the universe, the scale factor, that gives you all kinds of fluctuations in the perturbations of your fields. And that leads to basically the prediction that you don't have a smooth universe created. This is the Big Bang, and this is basically the picture for the zero mode. Hartle and Hawking proposed something like this. So you get small fluctuations, which would be in the Gaussian fields we see in the CMP, or the Gaussian fields, which is the state which inflation starts with. But what we find is that rather than that, you get highly violent perturbations which are favored with respect to the small fluctuations, which would basically say that you would see black holes everywhere. So the key point is that this mathematics applies to a wide range of fields. Some you might care about, some you care less about, but it makes these things predictive. So now you can just ask the question, you can say, what does the theory predict? And you can learn what its results are, and you can make some progress. So this is led to a lot of debate at the time, and still people are trying to fix it. Tweaking the theory so that you get these Gaussian fluctuations out. But I haven't seen a convincing solution which doesn't assume yet something else. So just in conclusion, using catastrophe theory, which is just this very small extension from just maxima and minima saddle points to these general critical points, you can make a lot of progress in non-perturbative physics. So you can do it in logical structure, where you can try to recover the filaments in the walls and the clusters. You can do it for the path integrals, where you find that if you actually evaluate these path integrals for simple models in real time, you get a beautiful interference pattern, which you can study and try to understand. You can do it in lensing, where we talked earlier today about geometric optics lensing. But if you do wave optics lensing, if you can actually observe it, then you have a lot more rich environment, and you can measure more because there are a lot more features in the signal. And this is all accessible by just extending your theoretical knowledge a little bit to include these 7 elementary catastrophes, which I find just very exciting. So you can do a lot with very little. So thank you very much for your
Thank you very much.